So, here we continue with a discussion on minimization on the number of states in a finite state machine. So, if you recall, in our last lecture we discussed that given a finite state machine, how we can reduce the number of states. We talked about the notion of an implication chart, how we can fill up entries in the implication chart, and using that how we can decide whether two states are equivalent or not. So, in this lecture we continue with a discussion. This is the second part of lecture on the minimization of finite state machines. Now, here we basically discuss first the concept of equivalence of two finite state machines. Earlier we talked about a single finite state machine and we explored whether two states S I and S j are equivalent or not. Now, we are saying that we have two different finite state machines, let us say N 1 and N 2, and we do not know whether the two machines are equivalent or not, meaning that they represent the same specification or not. So, we will have to find out in some way that some state x of the first machine and some state y of the second machine, whether they are equivalent or not. And if we can find out such a one to one correspondence, then we can only say that the two machines are equivalent. So, the concept that you follow is very similar to that of the implication chart, and we shall be explaining with the help of examples. Now, first let us look at the notion of equivalent FSMs. Two finite state machines N 1 and N 2, that I have said that I have two FSMs, I am calling them as N 1, other one I am calling them N 2. They are defined to be equivalent if for every state p that is there in N 1, there will exist a state q in N 2, such that these two states are equivalent. So, as I said, there will be a one to one correspondence. The first thing will be that the number of states in N 1 and the number of states in N 2 must be the same, and secondly there has to be a one to one correspondence between the states of the two machines. So, for every state p in N 1, there must be an equivalent state in q, and also conversely for every state s in N 2, there must be a corresponding state t in N 1. So, it has to be both ways. So, if we can show this, then only we can say that the two machines or FSMs are equivalent, and we shall be using a process which is very similar to implication table for verifying the equivalence. Let us take an example to illustrate the process, because it will be easiest. So, we consider two FSMs N 1 and N 2 as shown. Both of them contain 4 states. Here the states are A, B, C, D. Here the states are S 0, S 1, S 2 and S 3. Now, we want to have a pairwise checking between the states of here and states of here. Therefore, now our implication chart will look like a square. So, it will be something like this. We will be listing the states of the first machine along one side and the states of the other machine along the other. So, our implication chart will look like this, and we will be pairwise considering, means every cell of this chart. Like for example, between A and S 0, what we will see that we have a state A here, we have a state S 0 here. You see that if the input is 0, output is 0, input is 1, output is 0. So, outputs are 0 0. Here also the outputs are 0 0. So, we will have to write some entries here, we cannot put a cross, but you see between A and S 1, A is 0 0, this S 1 is 0 and 1. So, we can definitely put a cross here. In this way, we will be filling up this table in a manner very similar to an implication chart. Let us see. So, here I have shown, I am just explaining. So, on the top I am showing the two state tables. This is the first state table and this is the second state table. And let us see how we have filled this up. This is the first iteration. So, we have shown A, B, C, D along the columns and S 0 to S 3 along the rows. Between A and S 0, let us see, between A and S 0 what is happening. Okay, first let us see the ones where there are some entries between A and S 1, A and S 1, B S 3, A S 0. Between A and S 1, you see between A and S 1, B S 3, A S 0. I think there is okay, between just a second, A and S 2. I think this should be 1, there is a typographic error, yeah, this should be 1, it will be corrected. Between A and S 0 there is a cross because 0 1, 0 0, there is a cross. A and S 3 also you see, A and S 3, 0 0 0 1, there is a cross. First look at the crosses, B and S 1, B and S 1, B and S 2, 0 1, C and S 1. So, like this you just pairwise you compare and you fill up this table in a very similar manner. Okay. So, I have not actually verified this table, you can check it yourself. Let me do one thing, let me just take this original table and forget this table and let me just work out this chart here separately. Let me work out this chart separately here. So, on this side we have A, B, C, D, on this side we have S 0, S 1, S 2, S 3. Let us see from this table between A and S 0, 0 0 and 0 0. So, we can put B S 3, A S 1. Okay, I am only writing 3, okay, S I am not writing, B S 3 and A S 1, A S 1. Between A and S 1, 0 0 0 1. So, there will be a cross. Between A and S 2, 0 0 0 1, there also a cross. Between A and S 3, 0 0 0. So, B S 2, B S 2 and A S 3. Then B S 0, B and S 0, 0 1 0 0 across, B S 1, 0 1 0 1. So, C S 3, D S 0, C S 3, D S 0, B S 2, 0 1 0 1. So, C S 0, D S 2, C S 0, D S 2. Then B and S 3, B and S 3, 0 1 0 0, there will be a cross. C and S 0, 0 1 0 0, cross. C and S 1, A S 3, C S 0, A S 3, C S 0, C and S 2, C and S 2, A S 0, C S 2, A S 0, C S 2, C and S 3, they are different cross. D S 0 similarly, D and S 0, C S 3, B S 1, CS3 B S1, DS1 different, DS2 also different, DS3 CS2 BS3, CS2 BS3. So, this is the correct implication chart corresponding to this table, because these tables which are shown there are some typographic error somewhere. So, this you can try to figure out, but for this table the chart will be like this. Now, in the next step what you do, you explore this further, like A1 B3, you look A1, A and 1 it is already cross, right. So, in the next step this will also get crossed. B2 A3, B2 is fine, A3 is also fine. So, A3 is actually self. So, this you can cut it out, only B2 remains. Then this one C3 D0, C3 is a cross. So, this will also get crossed. C0 D2, C0 is a cross, this will also get crossed. Look at this A3 C0, A3 is something is there, C0 is a cross. So, this will also get crossed. A0 C2, A0 is a cross. So, this will also get crossed. And lastly, here C3 B1, C3 is a cross, this will get crossed. C2 B3, C2 is cross. So, this will also get crossed. So, you finally are left with a single entry B2, right. So, this way you can find out which pair of states are actually equivalent. So, if you see it is only B2, it will say this means that only you can find an equivalence between state B and S2, the others are not equivalent. So, we can say that machine N1 and this machine N2 they are not equivalent. Okay. But the example that I showed here, this was for some other state table. So, I leave it as exercise for you to find out that where this mistake was in the state table and for which state table this is coming, and the final equivalent states were like this, right. But the process is like this, the process is very similar, just using the implication chart you work out, and finally, whatever is left in this table that will tell you which state pairs are equivalent. And if you can find, like in this table shows, that 4 such correspondences for the 4 states, then you can say that the states are equivalent, right. Okay. Let us take another example. I am not working it out, but I am actually telling you how to do it. Suppose I have a problem like this. There are 2 machines where I can see in one machine there are 7 states, other machine there are 3 states, and someone asks you to check whether the machines are equivalent or not. Well, at first look you may tell that because the number of states are not the same, so they cannot be equivalent. But the next question is, the 2 machines that are given to you, there may be redundant states in those machines itself. So, you have not done any minimization. So, always your first step will be to reduce the individual machines as much as possible, and then you check whether the number of states are the same or not. If they are not same, no need to check. If the number of states are same, then only you follow this process and test whether there is an equivalence corresponding to state pairs in the 2 machines. So, here the process will be like this. For the machine N1, you will have to first carry out a state minimization. And the same thing you will have to follow for state or for the machine N2. So, after you have minimized it, then whatever machines you get, these 2 state tables. So, if you find that the number of rows are the same, then you follow the process and test whether they are equivalent or not, right. So, I leave this as an exercise for you. You can basically try this out and check whether you are getting this equivalence or not. Okay. So, whatever we have seen so far concerns the equivalence of states in a FSM or in general equivalence of two FSMs totally. Now, what we have not mentioned so far, there can be some instances, some problems where there can be the notion of some do not care inputs. Some inputs or some output values can be do not cares. So, while we are doing this state minimization, how do you handle do not cares? Let us take an example to illustrate this, and such specifications where there can be do not cares are in general referred to as incompletely specified machines. So, this specification is not complete. Some of the information like inputs and outputs are not mentioned, they are called incompletely specified machines. Now, what do you mean by incompletely specified machines? There are two things. First is that the number of input combinations that can be applied can be a subset of all possible input combinations. Like for example, I have a circuit, let us take an example. Let us say there are 3 inputs. Because there are 3 inputs, this is an FSM that we are trying to design. Okay? This is an FSM. Because there are 3 inputs, there can be 8 possible input combinations 2 to the power 3, but let us assume out of this 2 to the power 3 only 3 input combinations are valid, which means during normal operation only one of these 3 input combinations can come. So, when you are designing the FSM, the remaining 5 inputs will be regarded as do not cares. So, I can suitably fix them depending on my convenience when I am doing state minimization. So, they can be set to 0 or 1 as per my convenience. Okay? So, other input combinations make it treated as do not cares. So, in general we say that an FSM is incompletely specified where the next state and also the output values are not specified for all input combinations. For some of them they are not specified, but we have seen earlier during state minimization we are looking at the outputs and also the next states. You see, more states we can club together, that is better for us because our FSM will get smaller. We can find out equivalent states. So, the next state and the output we can suitably set during the process of minimization, so that more states can be merged together and the FSM can become smaller. This is the basic idea I shall be illustrating with the help of an example, okay? But the idea is basically this. Let us see, let us take an example. This is a very simple example, I am just illustrating it. Suppose we are trying to design this sequential circuit B. Okay? Now, the input of this circuit is coming from some other circuit, let us say A, and this input we are calling as X, and the output is going to some other circuit C, this output we are calling as Z, right. Now, how this circuit is working? Let us say that this circuit A is generating a serial bit stream. So, X is not a parallel number, serially some bits are coming one by one, okay. One bit at a time in synchronism with a clock, the bits are coming. So, I am assuming that this circuit A can generate only 2 possible output sequences, bit patterns 100 and 110. And this sequential circuit is designed in such a way that when 100 is received, Z will be set to 0, and when 110 is received, Z will be set to 1. Now, you understand this situation. I am trying to design a circuit which is being fed with 3 bits in sequence, and out of the 8 possible combinations only 2 of them are valid. They are 100 and 110. Now, in one case the output should be 0 if 100 is received, and the other case the output should be 1. So, for the all remaining 6 cases, because such inputs will never come, so I can, as per my convenience, I can set the output to 0 or 1 whatever, because it will not matter, because those inputs will never come. And the other thing is that the output will become 0 or 1 once this entire sequence is received, but before that it does not matter, the output can be either 0 or 1. That also I can set according to my convenience. Only at the end of the third cycle the output will denote that whether one of those two strings have been received or not, 0 or 1. Okay. So, what I am saying is that assume that the circuit C ignores the value of Z at all other times. Only when these 3 ones have been received, then only the output will be either 0 or 1, depending on which of the two sequences have been received. So, the possible input output sequence I can depict like this. The first circuit is generating X, which can be either 100 or 110. The others can never come, and the corresponding Z output only at the end it will be either 0 or 1. This T0, T1, T2 indicates the times, the clocks, but before that these two states are do not cares. I do not care what is coming here, but only I care what is the final value. Right. Now, depending on this I can create the state table, or first I think it will be easier to show the state transition diagram. So, here I require 4 states because I need to identify a 3-bit sequence. I start with an initial state. Suppose I get a 1, I move to state S1, but when I get the first one, the output can be do not care, that is why the output is dash. Dash means do not care. Now, I am in state S1 when the first one is received. Now, if the next bit is 0, then possibly 100 is coming, I move to state S2. So, again the output is do not care, but if the next bit is 1, I move to S3 because possibly 110 is coming, 1 again the output is do not care. But if 110 has actually come, then only my output is coming to 1, and if 100 has come, then also my output will be 0, right. So, the output is being generated only in these two cases. So, all other you can see they are do not care combinations. Just like for example, from S2 I am only showing an output transition when there is a 0, but what will happen if the input is 1? This is do not care. So, I can put any next state as per my convenience, right. These are the places where I can play with, and for this state transition diagram the corresponding state table is this. So, directly this is a 1-to-1 mapping. For S0, if x is 0, nothing is mentioned, that is why dash comma dash, it is not shown. Next state is also undefined or do not care, output is also do not care, but only for x equal to 1, 1 comma dash, that means S1 comma dash for x equal to 1, S1 with dash. Similarly, from S1 there are 2 states from 0 and 1. So, there are 2 entries. From S2 there is a single for 0, for 1 not specified, similarly for S3. Okay. Now, from this state transition diagram or state table, now we can fill up the do not care suitably, so that we can carry out minimizations effectively. Now, all those dashes which are there, so here in this blue that I have shown bold, these are the ones where we have filled them up suitably, like this dash we have filled up with S 0, this dash with S 1, this dash with S 3. So that some states can be made equivalent. Similarly, this output has been made 0, this output has been made 1. So, this you can arbitrarily fill up, and your objective will be to make as many states equivalent as possible. So, accordingly the next states and the outputs you can set to either 0 or 1. So, I am just showing an example here. Now, in an ad hoc way I have filled it up as per my convenience. So, with this assignment, let us see how the implication chart will look like. There are 4 states, S 0, S 1, S 2 along here, S 1, S 2, S 3 along here. Let us see S 0 and S 1. S 0 and S 1, you say they are differing here 0 1 in their output. So, we have put a cross. S 0 and S 2. See, since S 0 or S 2 I have put a tick just to make them equivalent. You see, there was this was S 0 0, I had made it S 0 0 just to make them equivalent. Similarly, S 1 dash I have made it S 1 just to make them identical. Because they are now identical, you can mark a definite tick here, and S 0 is 3, 0 1 they are different. So, this is also x. S 1 S 2, S 1 and S 2 1 0 they are also incompatible. So, a cross. S 1 S 3, so S 1 S 3 1 dash outputs are same, but S 2 S 0 S 3 is same, S 3 S 3, S 2 S 0. So, we have marked it S 2 S 0, and S 2 and S 3 is also different 0 1 x. So, we have obtained the implication chart like this. Now, after we have obtained like this, let us look at S 2 S 0. S 2 S 0 are also equivalent, okay? S 0 S 2. So, this one also you will be changing it to a tick. So, finally, S 0 and S 2 will be equivalent, and S 1 and S 3 also will be equivalent. So, S 0 and S 2 you can merge together into a single state, S 1 S 3 you can merge together into a single state. So, first let us look at the state table. So, if you merge S 0 and S 2 together, you see S 0 remains same, S 0 0 and S 1 dash, S 2 is merged with it. So, S 2 is gone. So, S 1 S 3. So, S 1 is S 2 1, now S 2 has become S 0. So, it will become S 0 1, S 3 dash, S 3 is now gone, S 3 has become S 1. So, it is S 1 dash, and S 3 is also same. So, this is the reduced table, and the reduced state transition diagram will look like this. There will be only 2 states. From S 0, if the input is 0, you remain in S 0 with an output 0, 0 0. If the input is 1, you go to S 1 with output do not care. When you are in S 1, if the input is 0, you remain in S 1, you go to S 1 this edge with the output 1, but if the input is 1, output is do not care, you remain in S 1. So, for this specification of the problem, this FSM can be reduced drastically in size, as you can see, and the final design will become much smaller. So, essentially what we have seen is that in the process of state minimization, given a FSM, a state table, we can reduce its size. We can use the same principle to identify whether 2 FSMs are equivalent or not. And lastly, we have mentioned if the FSM is incompletely specified, there are many examples where we do have such incomplete specifications, then we can suitably set the do not care entries in the state table such that as many of the states can be marked as equivalent. In the example that we cited, only we could have made 2 such states were made equivalent by suitably filling them up, and the net result is that our final FSM specification becomes simpler and our circuit becomes much smaller, right. So, with this we come to the end of this lecture, and we have completed our discussion on minimization of finite state machines. Now, in our next sequence of lectures, we shall be looking at the design of some very specific finite state machines or sequential circuits, namely registers and counters, which are very useful building blocks in designing complex systems. So, this discussion we shall be starting in our next lecture. Thank you.